Good morning, students. Myself, Vijay Shankar from EC Department, Chevrolet Engineering College. Today, we are going to discuss about the last topic in this fourth unit, magnetostatics. This is a time-varying Maxwell's equation for the time-varying fields. In yesterday's class, we discussed about the boundary surfaces between the dielectric and dielectric for electrostatics, nothing but electric field and the electric flux. In this class, we go for the discussion about the boundary conditions or the boundary surfaces between dielectric and dielectric for the magnetic field and the magnetic flux. Okay, or boundary conditions for the magnetostatics. See, as we discussed in the last class, yesterday's class, the boundaries between dielectric and dielectric and conductor and the dielectric, we got the continuous and the discontinuous for dielectric and the dielectric. Here also, you can find out the tangential component for the magnetic field and the normal component of the magnetic field, and thereby you can write the equations in terms of the magnetic flux in terms of the magnetic fields. The conditions of the magnetic field existing at the boundaries of the two media when the magnetic field passes from one media to the other media is called boundary conditions for magnetic fields, or simply magnetic boundary conditions. When we consider the magnetic boundaries conditions, the conditions of B bar and H bar are studied at the boundary. The boundary between the two different magnetic materials is considered. The boundary between the two different magnetic materials is considered to study the conditions. The P bar and H bar at the boundary, both the vectors are resolved into two components. One is the tangential to the boundary and normal to the boundary. Consider a boundary between the two isotropic homogeneous linear material with a different permeabilities. So dielectric and dielectric here. It's not the dielectric, two different permeabilities, mu1 and the mu2. So dielectric means it's epsilon1 and epsilon2. Here the different, consider a boundary between the two isotropic homogeneous linear material with a different permeabilities, mu1 and the mu2 as shown in the figure. For the boundary line, both the mu1 is there, and below the line the mu2. To determine the boundary condition, let us use the closed path of the Gaussian surface. Closed path of the Gaussian surface means to find the tangential component of the magnetic. Consider a rectangle as we use to find the tangential component of electric field also. The rectangle half part is in the medium 2 and half part is in the medium 1. It is AB and B2 half part delta H by 2. Delta H by 2. And 2 to C, another delta H by 2. The total height of the BC is delta H. Okay, the downward direction. And C to D, the opposite direction of A to B. Width is the same, delta omega. And B to A, the direction now the upward direction compared to the BC. And here also the half part is in the direct, half part is in the medium 2 and half part is in the medium 1. In the medium 1 is delta H by 2. And in the medium 2, permeability, another delta H by 2. The total height of D to A is DH. To find the tangential component, a tangential line on the boundary H tan 1 and is a parallel to that of the AB and the DC. And to find the normal component of magnetic field is parallel to the BC and the AD, because this line is parallel to the BC and the AD, and the tangential component to find the magnetic field H tan 1 bar is parallel to that of the AB and the DC to get the H bar, and similarly B tan and the B normal. Okay. In the electric field, we use the integral E bar dot dl bar. Now here you can use the H bar dot dl bar is equal to ampere circuit law. Okay, ampere circuit law, and the gas law is a B bar dot ds bar to find the normal component using the cylindrical here. Half part of the cylinder is in the medium 1, the mu 1, and the medium 2 in the mu 2. Here the gas law of can use the two equations. One is P bar dot ds bar, the Gauss law of magnetic field. Another one is Ampere circuit law, H bar dot dl bar. H bar dot dl bar is equal to I enclosed. These two equations related to the magnetic field or the magnetostatics, and we derive the equations, the tangential component of electric and the electric field and electric flux density. We use the Gauss law, the D bar dot ds bar is equal to Q, and E bar dot dl bar is equal to 0 there. Okay. Now let us see the boundary conditions for the normal component. First, the boundary conditions for the normal component. To find the normal component of B bar, select a closed Gaussian surface in the form of a right circular cylinder. For normal component means you can consider a right circular cylinder as shown in this figure. Let the height of the cylinder be the delta H and be placed in such a way that delta H by 2 is in medium 1 and remaining delta H by 2 is in the medium 2. Also, the axis of the cylinder is the normal direction to the surface. Okay. Here we can use the Gauss law of magnetic field. Gauss law of magnetic field is the integral B bar dot ds bar is equal to 0, because in the monopole there is no any existing here. The 0 will get. The lateral surface must be evaluated over the three surfaces: the top, bottom, and the lateral. Okay. The integral top B bar dot ds bar plus integral bottom B bar dot ds bar plus the integral lateral B bar dot ds bar is equal to 0. As we are very much interested in the boundary conditions, reduce the delta H to the 0. As the delta H tends to the 0, the cylinder tends to boundary and only the top and bottom surfaces contribute in the surface integral. So delta tends to the 0 means the lateral side becomes a 0. So in the three integrals, we have only the top and the bottom. The top is the B bar dot ds bar plus the bottom B bar dot ds bar. And the lateral side, as we reduce the delta H tends to 0, we considered only the lateral and top and the bottom plus the 0 is equal to 0. And this integral top, write the B bar as a B normal. Top means a BN1 we consider here, the integral ds plus the bottom is a BN2 because in the medium 2 integral ds. The surface integral considered as a equal to the delta S. Okay, so BN1 delta S minus BN2 delta S is equal to 0. Now the BN1 delta S is equal to BN2 delta S. So delta S and delta S cancel. We got both are equal. BN1 is equal to BN, or BN1 bar is equal to BN2 bar. And the relation between the B and the H, B bar is equal to mu into H bar. So BN1 bar is equal to the magnetic flux, the normal is equal to, because it is a medium 1, mu1 into H1 bar, HN1 bar, the normal component of the magnetic field and the normal component of the magnetic flux. Similarly, the BN2 bar is equal to, in the medium 2, that is a mu2 HN2 bar. So we got the BN1 is equal to BN2, means combine the, equate the two functions, mu1 HN1 bar is equal to mu2 HN2 bar. Therefore, the ratio between of HN1 bar by the HN2 bar is equal to mu2 by the mu1. Okay, mu2 by the mu1. Got it, Marshall? This is a continuous and this one is a discontinuous. Continuous and this one is a discontinuous. Got it? See here, the integral of the top surface, the integral b bar dot ds bar is equal to bn1, the integral ds bar, bn1 into ds, bn1 into ds, not the ds, the delta s. Okay. Similarly, for the top, we got the bn1 and delta s. Similarly, for the bottom surface also, bn2 delta s. The lateral side is a 0. The lateral side, the b bar dot ds bar is equal to 0. Substitute all these equations, bn1 delta s minus bn2 delta s is equal to 0. Both are in the opposite directions. Bn1 delta s is equal to Bn2 delta s. Okay, why I wrote that is a minus means one prop is in the above medium 1 and the below the medium 2, and the direction is different. The bottom it is a upward direction and the top is in the downward direction. Okay, so Bn1 is equal to Bn2. Thus, the normal component of B bar is continuous. Thus, the normal component of B bar is continuous at the boundary. So, continuous at the boundary, Bn1 is equal to Bn. As the magnetic flux density and the magnetic field are related by each other, we got the B bar is equal to mu into H bar. B bar is equal to mu into H bar. So, H1 Hn1 by the Hn2 is equal to mu2 by the mu1. Okay. Hence, the normal component of H bar is not continuous at the boundary. Is not the continuous at the boundary. The field strength is in two media are inversely proportional to their relative permeabilities. Inversely, see H1 is a 1 by mu1 and H2 is a 1 by mu2. So it is not continuous, it is a discontinuous set. And the field of the strength in the two medium are inversely proportional to their relative permeabilities. Got it, my students? As we got the similarly, the Dn1 is equal to Dn2 in the electrostatics or the electric field, and En1 by the En2 is equal to epsilon 2 by the epsilon. Now, you go for the finding of the tangential component. The tangential component, according to the Ampere circuit law, in the electrostatics, we take that as a E bar dot dl bar is equal to 0. Now, according to the Ampere circuit law, H bar dot dl bar is equal to I. As we are assuming a rectangle form, half part is A, B, C, and the D. Half part is in the medium 1, that is a mu1. Half part is in the medium 2. The width is delta omega. Height is a delta h. So h bar dot dl bar is equal to I. Considered a rectangular closed path A, B, C, D as shown in the figure. It is traced in the clockwise direction AB, BC, CD, and DA. This closed path is placed in a plane normal to the boundary surface. It divided into the 6 parts. What is that 6 parts? First one is AB, A and the B. And there is a boundary is there. At the boundary, the B21, B21, and 1-C, 1-C here also, 1-C, and C-D, the fourth integral, and D-2, D-2, fifth integral, and the sixth integral is A2 H bar dot dl bar is equal to I. Got it, Matis? It is clear that the closed path is placed in such a way that its two sides AB and ED, AB and CD, okay, are parallel to the tangential direction, because the tangential component you can take like this, AB and CD is tangential components, and it is a parallel also to the surface, while the other two sides are the normal to the surface of the boundary. This closed path is placed in such a way that half of the position is a medium 1 and remaining half part is in the medium 2. The medium 1 is a half part and the medium 2 is a half part. The rectangular path is an elementary rectangular path with elementary height delta H and elementary width delta omega. Thus, the overall over small width delta omega H bar can be assumed the constant, say H tan 1 in the medium 1 and H tan 2 in the medium 2. Similarly, over a small height delta H bar. And H bar can be assumed the constant, say Hn1 in the medium 1 and Hn2 in the medium 2. Got it, my friends? Now assume that the K bar is a surface current normal to the path. Means see, whenever in the magnetic field I into dl bar cross AR bar, the function, then for the surface we are taking the K bar cross AR bar into ds, and for the volume integral J bar cross AR bar into ds. So for the surface current, K bar is a surface current normal to the path. Also, it is clear that the normal and the tangential component in the medium 1 and the medium 2 are opposite direction. Definitely, AB and the CD is in the opposite direction, and BC and DA is in the opposite direction. Got it, my students? And it can be written as the current, whatever we are saying, that is a current surface, K is the surface current normal to the path, K into delta omega or d omega, let us take here. And the first integral, what we are taking here, the 6 integrals are there. The first integral, A and B, let us assume here the A and B, H tan 1, because it is in the medium 1, H tan 1 and the delta omega. For this integral, we got here the H tan 1 delta omega. For the second one means this line is parallel to the tangential component, and this line is parallel to the normal component. Okay, Hn1, and this line is H tan 1. Got it, my students? Up to the B21 only, it is in the mu1, in the medium 1. So B21 plus, I'm writing here, B21, Hn1, because it is a parallel to the normal, Hn1, and integral dl bar is a half of the part is in the medium 1, means the delta H is divided as a delta H by 2 the delta H by 2. So you'll get the delta H by 2 here. Plus, and 1-C. 1-C is in the medium 2, means let that is also the normal component only, Hn2 delta H by 2. Got it, my students? Hn2 delta by 2. We got the 3 integrals. Another 3 integrals is C to D. C to D, observe here, the C to D is there. This is in the medium 2. So C to D is parallel to the tangential component. So you take that as H tan 2. Understood, but understood. Don't confuse here. Because in the medium 1, I take the integral A to B is a H tan 1 and multiplying the delta omega. Now I'm taking the fourth integral C to D because it is in the medium 2. I take that H tan 2 and opposite the direction. See here, A and B is in the positive direction and it is opposite direction. So minus delta omega. Okay, that is a fourth integral. And fifth integral you can observe here. Fifth integral, half part A to D to 2. D to 2, that is a delta H by 2. And it is a parallel to the normal component. And it is in the medium 2. So I am writing here the HN2 opposite to that of 1 to C. 1 to C. 1 to C already taken, that is a delta H by 2. And the direction is opposite. So minus delta H by 2. Understood, my dear students? So don't confuse here. So 1 to C is in the positive direction. Taking that, it is a delta H by 2 is a positive means. D to 2 you can take as a delta H by 2 is a minus. Okay. Both are in the medium 2, HN2 and HN2. If suppose you can take here, it is a minus delta H by 2 minus. You can take here as a plus delta H by 2. And the last integral, that last integral is in the medium 1, 2 to A. 2 to A. H bar dot DL bar. DL bar is a delta H by 2. And H bar is normal to the parallel to the normal line. So you can take HN1, and it is opposite the direction of B1 and 2A. Opposite direction. So minus delta H by 2. Delta H by 2 is it's all totally equal to the I. What is that I? The surface current normal direction, K bar or the K dot delta omega d omega. Understood, my dear students? All the integrals of how I wrote, because it is a parallel A, B and the CD. Take the, whenever you can integral, the H value is a tangential component. BC and the DA is a normal components. And that depends upon the direction. You can take one as a positive means, another one is a minus. And simplify here. To get the conditions at the boundary delta H tends to 0, thus K dot dW is equal to delta H tends to 0 means all the delta H terms is a 0. We have only the delta omega means delta H tends to 0. The second integral is a 0, third integral is a 0, and fifth integral is a 0, and sixth integral is also the 0. Or otherwise, you can see HN1 delta H by 2 minus delta H by 2, plus and minus get cancelled. Or delta H by 2 and minus delta H by 2, the HN2 and HN2 all get cancelled. And finally, we have H tan 1 delta omega minus H tan 2 delta omega. And this is also delta omega only, my students. Whenever we can write it as an integral value, the dot K dot delta omega, the K value and integral d omega you can take as a delta omega. And both sides of delta omega get cancelled. H tan 1 minus H tan 2 is equal to K. Got it, my students? And H tan 1 minus H tan 2 is equal to A and 2 bar cross. It is in the terms of the vector format. If it is in the normal components, scalar terms, H tan 1 minus H tan 2 is equal to K. In a vector form, we can express the above relation by a cross product as, this is only the scalar, my dear students. H tan 1 minus H tan 2 is equal to K. And if it is a relation, the scalar only, B is equal to mu into H. So B tan 1 is equal to mu1 into h1. Why I wrote the mu1? 1 means the medium 1 is a mu1 or b tan 2 is equal to mu2 into h tan 2. Already we know the h tan 1 minus h tan 2 is equal to k. So h tan 1 is equal to b tan 1 by the mu1 and h tan 2 is equal to b tan 2 by mu2. So subtract these two functions and equate to the k. So b tan 1 by the mu1 minus b tan 2 by the mu2 is equal to k, and in the scalar form. Got it, my dear students? In the vector form, you can write this in the vector form. H tan 1 bar minus H tan 2 bar is equal to k cross an bar, that is from 1 to 2, where an bar is a unit vector in the direction normal to the boundary from medium 1 to the medium 2. 1 to 2, the medium 1 to the medium. So in terms of the B bar, the tangential component is related to the two permeabilities, B tan 1 by the mu1 minus B tan 2 by mu2 is equal to K. It's in the scalar form. Okay, my dear students. Now consider a special case that the boundary is free of current. The free of current. In other words, the medium are not conductors. So the k is equal to 0. The equation becomes h tan 1 minus h tan 2 is equal to 0, or h tan 1 is equal to h tan 2. And similarly, in this equation also the k is equal to 0 means, in this equation of the k is equal to 0, b tan 1 by mu1 is equal to b tan 2 by mu2. Okay. Therefore, the ratio between of the b tan 1 by the b tan 2 is equal to mu1 by the mu2. Got it, my students? In the medium one, from the equations here, the 15 and 16, it is clear that the tangential components of h bar are continuous. H bar are continuous means both are equal, means it's a continuous, my students. H tan 1 is equal to h tan 2, it's a continuous. And this one is not a continuous. Not a continuous, but it is inversely proportional. Okay. H bar are continuous, while the tangential components of B bar are the discontinuous at the boundary, with the condition that boundary is in the current free. When the k is equal to 0 only, they can saying that h tan 1 is equal to h tan 2, both that are continuous, and b tan 1 and the b tan 2 are the discontinuous at the boundary when the current is free. K is equal to 0. Let the fields make an angles of alpha 1 and alpha 2 with the normal to the surface interface B1 and the B2. Tan alpha 1 is equal to, let us take this right angle triangle, my dear students. Consider this a right angle triangle. Okay. Tan alpha 1 is equal to opposite side by the adjacent side. Opposite side is a B tan 1 by the Bn1. And similarly in the medium 2 with an angle alpha 2. Again, you can take this as one of the right angle triangle. Opposite side is a B tan 2 and adjacent side is a Bn2, sorry, because it is the medium 2. Tan alpha 2 is equal to and tan alpha 1 is equal to. Got it, my dear students? So simplify the ratio of tan alpha 1 and alpha 2 is B tan 1 by the Bn1, Bn2 by the B tan 2. Okay, because of Bn1 is equal to Bn2, we already derived the expression, would get cancelled. Tan alpha 1 by the tan alpha 2 is equal to B tan 1 by the B tan 2, that is equal to B mu r1 by the mu r. What it matters, friends? Why we take this? There's practically when the fields crosses a medium of high mu r to the low mu r, then the magnetic fields B bar and H bar are always perpendicular to the boundary. For this, we are taking that in terms of the alpha and alpha 2. Thus, practically when the fields crosses a medium, when fields crosses a medium from high permeability mu r to the low permeability the mu r, then the magnetic fields B bar and H bar are always perpendicular to the boundaries. Okay. So with this completion of the boundary surfaces of the magnetic and the electric, we go for the conclusion of all the boundaries, boundary conditions for the time varying fields. Boundary conditions for the time varying fields, both the electric and the magnetic. The relation between of the electric flux density and electric field intensity, magnetic field flux density and the magnetic field intensity can be explained with the help of point form or the integral form of the Maxwell's equations. The field equations, the Maxwell's equations are useful in the determining the conditions at the boundary surfaces of two different media when we apply the concepts of linear, isotropic, and the homogeneous medium. Consider the boundary between the medium 1 with parameters epsilon 1 and the mu 1 and sigma 1. Sigma is a conductivity and epsilon is a permittivity and mu 1 is a permeability. This totally these three parameters are in the medium 1. These three parameters in the medium 1 because medium 1 in the dielectric, not the dielectric, let us take this at medium 1 upwards. And in the medium 2, we consider the dielectric, that is epsilon 2, and permeability mu 2, and the conductivity also sigma 2. Got it? In general, the boundary conditions for the time varying fields are same as those for the static fields. Thus, the boundary, referring the boundary conditions for the static electric magnetic fields, we can write as E tan 1 is equal to E tan 2. It's a continuous. The tangential component of electric field intensity E bar is continuous. And the tangential component for the magnetic field is also H tan 1 is equal to H tan 2. That is also the continuous. The tangential component of the magnetic field is also continuous. H tan 1 is equal to H tan 2. The tangential component of magnetic field intensity is continuous across the surface except for the perfect conductor. Okay. That is H tan 1 is equal to H tan. And at the surface of the perfect conductor, the tangential component of magnetic field intensity is discontinuous. At the surface of the perfect conductor, means there is no any current. K is equal to 0, then H tan 1 is equal to H tan. But it is a perfect conductor. H tan 1 minus H tan 2 is equal to K. Okay, my dear students. The third point, the normal component of electric flux density is continuous. dN1 is equal to dN. If the surface density is a 0, the rho s is equal to 0. If the surface charge density is a non-zero, it is a discontinuous. dN1 minus dN2 is equal to rho s. Okay, this is a discontinuous when it is not equal to the 0, and it is equal to the 0, then both the normal components of medium 1 and the medium 2 is equal in the electric flux density. The same way in the magnetic flux density also, the Pn1 is equal to Pn. Got it, my dear students? The tangential and the normal components of electric and the magnetic field, E tan 1 is equal to E tan 2, H tan 1 is equal to H tan 2, both are continuous. And if it is a discontinuous for the magnetic field, the K is not the 0, H tan 1 minus H tan 2 is equal to K. And for the normal components, for continuous and the discontinuous, dN1 is equal to dN2 for electric flux, and non-zero term of the rho s, dn1 minus dn2 is equal to rho s. This is a continuous and discontinuous. The normal component of the magnetic flux density is a continuous. Bn1 is equal to Bn2. Got it, my students? With this, the completion of the completion of magnetostatics and the Maxwell's equations for the time varying fields. Means fourth unit is fully completed. The theory part of the fourth unit is fully completed. Got it?